June 7th, 1944. Normandy coast, France. The storm had passed, leaving behind a grey sky and choppy waters that slapped against the strange metal structures emerging from the sea. Oberleutnant Hans Weber stood on the cliffs above Arromanches, binoculars pressed to his face, watching as thousands of tons of cargo flowed onto French soil through what appeared to be a harbour that hadn't existed 48 hours earlier. He believed he was witnessing impressive but ultimately temporary Allied ingenuity, something his engineers could understand, replicate, and ultimately defeat. He had no idea he was staring at the physical manifestation of industrial capacity so vast it would reshape his understanding of what was possible in modern warfare. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What Weber and his fellow German engineers were about to discover would transform them from confident professionals into men confronting an uncomfortable truth. They hadn't just underestimated Allied capabilities, they had fundamentally misunderstood the nature of the conflict they were fighting. The artificial harbours at Normandy would become their education in the brutal mathematics of total industrial war. Weber had graduated top of his class from the Technical University of Berlin in 1936, specializing in coastal engineering and fortification design. His credentials were impeccable, his understanding of harbor construction encyclopedic. He had helped design portions of the Atlantic Wall, had calculated load-bearing capacities for dozens of defensive positions, had consulted on the placement of obstacles along every major beach from Norway to Spain. When his commanding officer, Major Friedrich Hartmann, ordered him to assess the Allied harbor structures, Weber felt confident. He understood harbors. He understood concrete and steel. He understood engineering. The morning of June 8th brought clearer skies. Weber assembled his assessment team. Hauptmann Otto Schneider, a structural engineer who had built bridges across the Rhine, Lieutenant Karl Fischer, a naval architect who had worked in Hamburg's shipyards, and Unteroffizier Paul Richter, a construction foreman with 20 years of practical experience in marine engineering. They were professionals, men who dealt in specifications and calculations, not propaganda or wishful thinking. Then Schneider said, his voice carrying an edge of professional curiosity, "We should begin with the structures closest to shore and work our way out. Establish the basic engineering principles before assessing the larger installation." They made their way down the cliff path, passing through positions where their own troops had fought desperately just days earlier. The scale of the Allied landing was evident in every direction, but Weber forced himself to focus on the technical challenge at hand. Emotion had no place in engineering assessment. Facts, measurements, calculations, these were the tools of understanding. The first structure they examined was a massive concrete caisson, a floating box that had been towed across the English Channel and sunk into position to form a breakwater. Weber ran his hands along the concrete surface, noting its composition, its thickness, its reinforcement patterns. Fischer took measurements while Richter sketched diagrams, his practiced hands capturing proportions and connections with quick, efficient strokes. "This is Phoenix construction," Weber observed, using the Allied code name they had learned from intelligence reports. Reinforced concrete approximately 60 feet high, 200 feet long. He paused, calculating in his head. Displacement approximately 6,000 tons when floating. Wall thickness suggests it was designed to withstand significant wave action. But Schneider was looking past the individual caisson to the line of identical structures stretching along the coast. He began counting, his lips moving silently, then counted again as if unable to believe his initial calculation. There was a long pause before he spoke. 31 of these structures, Schneider said quietly, just in this section, each one displacing 6,000 tons. That's over 180,000 tons of reinforced concrete that had to be built, floated, towed across open water and positioned with precision. The implications hung in the air between them. Weber knew exactly how long it took to pour, cure and finish that volume of concrete. He knew the amount of steel reinforcement required, the number of skilled workers, the coordination of materials. For a moment, none of them spoke, each man running calculations that led to uncomfortable conclusions. Fischer broke the silence, his voice carefully neutral. "The concrete quality is excellent. No significant cracking despite the towing and sinking operation. The engineering is sound, very sound. They moved along the breakwater, examining connection points, studying how the caissons had been joined to create a continuous barrier against the sea. Every detail spoke of thorough planning and flawless execution. But it was when they reached the end of the Phoenix line and saw what lay beyond that Weber felt the first tremor of something deeper than professional respect. Stretching into deeper water was a different kind of breakwater, this one made of ships. Not old hulks or damaged vessels, but ships that had clearly been seaworthy, deliberately sunk in precise positions to form a barrier. Weber counted them, his trained eye estimating tonnage and type. Liberty ships, older merchantmen, a few naval vessels past their prime. 53 ships, he calculated. Perhaps 55. Just here, just for this installation. They sank usable ships, Richter said, his foreman's practicality unable to mask his disbelief. Dozens of them. Ships that could have carried cargo or troops or supplies. They sank them just to make a temporary breakwater. The word temporary echoed strangely. Weber looked back at the massive concrete caissons, at the sunken fleet, at the scale of engineering that surrounded them. Nothing about this felt temporary. This was infrastructure built with the same permanence as a major civilian harbor, except it had been constructed in months, transported across open ocean, and installed in days. Let's examine the pier systems, Weber said, pushing the team forward. Understanding the problem completely was the first step toward solving it. The piers were perhaps even more remarkable than the breakwaters. Enormous steel roadways stretched from the beach out over the water, supported by massive floating pontoons called beetles. Each beetle was a cruciform structure of welded steel, hollow and buoyant, rising and falling with the tide, while the roadway above remained level through an ingenious system of adjustable legs. Fisher measured one of the steel spuds, the vertical legs that slid through the pontoon to anchor on the seafloor. Each one is nearly a foot in diameter, he reported. High-grade steel, precision machined to slide smoothly while bearing enormous loads. He looked up at the roadway above, calculating the tonnage requirements, the bearing loads, the tidal variation accommodation. This is exceptional engineering. Weber climbed onto one of the pontoons, feeling it respond to the wave action with a gentle, controlled motion. The welds were perfect. The steel plate uniform and high quality. He opened his notebook and began listing specifications, but found himself adding comments that went beyond mere technical description. Each pontoon approximately 60 feet long, he wrote. Steel plate thickness, approximately 3/4 of an inch. Estimated weight per unit, 23 tons. He paused, then added, build quality consistent with major naval construction. No evidence of rushed production or material substitution. Schneider was examining the roadway connections, the ingenious hinges that allowed the pier to articulate as the pontoons rose and fell. Look at this joint design, he called to the others. It accommodates vertical movement of up to 20 feet while maintaining structural integrity, the precision required for this fabrication. He trailed off, running his hands over the machined surfaces. They walked the length of one pier, measuring as they went. 700 feet, 800, 900. The structure stretched nearly a mile from shore to deep water, where Liberty ships were moored, their cranes offloading cargo directly onto trucks that drove along the floating roadway. Weber counted the piers. 6 major structures at this site alone, each capable of handling multiple ships simultaneously. The mathematics became inescapable. Each pontoon was 23 tons of fabricated steel. Each pier required dozens of pontoons, plus the roadway sections, plus the specialized equipment for anchoring and adjustment. 6 piers meant thousands of tons of precision-engineered components, all built to identical specifications, all transported and assembled under combat conditions. That afternoon, they examined the smaller craft that serviced the harbor. Powered pontoons called rhinos that ferried vehicles from ships to shore, specialized tugs, floating cranes, workshop vessels equipped to handle on-site repairs. Every element of a major port facility had been replicated in mobile, temporary form. Except as Weber studied the construction quality and engineering sophistication, the word temporary began to feel like a dangerous mischaracterization. Major Hartmann arrived as evening approached. his staff car navigating between supply dumps that seemed to grow larger by the hour. He found the assessment team sitting on a concrete caisson, surrounded by notebooks and sketches, their faces wearing identical expressions of troubled concentration. "Your initial findings," Hartmann demanded. "Can we replicate this technology? Can we disrupt the harbor operations?" Weber looked at Schneider, at Fischer, at Richter. They had discussed exactly these questions for the past hour, running through scenarios and calculations, each hoping one of the others would find the flaw in their reasoning that would make the conclusion less stark. "Major, we can replicate the individual technologies," Weber began carefully. "The concrete caissons are sophisticated but not beyond our capabilities. The floating pontoons are excellent engineering but use no secret techniques. The pier systems are clever but not revolutionary." "Then what's the problem?" Hartmann asked. "The scale, sir. The sheer, overwhelming scale." Weber opened his notebook, referring to figures they had compiled. "The concrete alone represents approximately 600,000 cubic meters of material, built, cured, transported and installed. The steel fabrications total somewhere between 30 and 40,000 tons, all of this built specifically for this operation, in addition to the standard equipment and supplies required for the invasion itself." Hartmann frowned, not yet understanding. "We have concrete, we have steel, we have engineers." Fischer spoke up, his naval architect's perspective adding crucial context. "Major, consider the Liberty ships we can see from here. The Allies are using them as cargo vessels to supply the harbor. Intelligence suggests they're producing these ships, each one 10,000 tons displacement, in approximately 45 days. We're watching them use standardized cargo ships as routine equipment, while simultaneously operating artificial harbor facilities that would take our entire engineering corps years to construct." "We're not fighting an enemy with better technology," Schneider added quietly. "We're fighting an enemy with so much industrial capacity that they can treat engineering marvels as expendable infrastructure." The Major was silent for a long moment, watching as another Liberty ship approached the pier, its holds full of supplies that would be offloaded, trucked inland, and used to sustain the Allied advance. Behind them, along the beach, supplies were stacked in dumps that stretched for miles. Fuel, ammunition, food, vehicles, equipment, all flowing through the artificial harbor at a rate that defied Weber's ability to calculate accurately. "Write your report," Hartmann said finally. "Complete technical specifications. But Weber, be honest in your assessment. We need to understand what we're actually facing, not what we wish we were facing." Over the following week, as the assessment team continued their detailed examination, the truth became progressively harder to avoid. They discovered that there were two complete artificial harbor installations, one at Arromanches and another further east that had been damaged by storms but was being rebuilt. They learned that the planning for these harbors had begun more than 2 years earlier, with full-scale testing of components in English and Scottish waters. They found evidence of coordination between British and American engineers, between military and civilian construction firms, between designers and manufacturers across an entire industrial alliance. The numbers accumulated into an overwhelming narrative. Weber calculated that the two Mulberry harbors, as the Allies called them, involved approximately 1.5 million tons of concrete and steel. The towing operation had required over 130 tugs, working in carefully coordinated waves. The installation had been accomplished while combat operations continued around them, but it was Fischer who identified the detail that transformed professional respect into something approaching existential dread. He had been studying the production schedules, trying to understand the timeline of construction. "Major," he reported to Hartmann with Weber and the others present, "the scale of production suggests that at peak construction, the Allies were dedicating resources equivalent to building a new port facility every week, not maintaining existing infrastructure, not repairing damaged facilities, but creating new harbor capacity at a rate of several million tons per year." Hartmann leaned back in his chair, the implications spreading through him like cold water. "For comparison," he said slowly, "what is our current total industrial output across all sectors?" The room was very quiet. They all knew the answer. They had all watched as Allied air raids disrupted production, as material shortages forced substitutions, as the Reich's industrial capacity struggled to meet even basic military requirements. The idea of dedicating resources to build infrastructure that would be used temporarily in a combat zone purely to enable further operations was almost incomprehensible. "What we're seeing here isn't just engineering," Weber said, choosing his words carefully. "It's industrial warfare at a level beyond anything in our doctrine. They're not trying to outfight us ship for ship or tank for tank. They're drowning us in productive capacity. They're building faster than we can damage, landing more supplies than we can interdict, creating infrastructure faster than we can destroy it." Richter, the practical foreman, added his perspective. "I've built harbors, bridges, fortifications. A project like this, in normal circumstances, would take 5 years of planning, 3 years of construction, and require every major engineering firm in a country to contribute. They did it in less than 2 years while simultaneously conducting the largest amphibious operation in history." Schneider had been studying casualty reports, cross-referencing them with supply flow data. "The harbor is currently operating at approximately 70% of planned capacity due to storm damage," he reported. "At this reduced rate, they're still landing 7,000 tons of supplies per day through the artificial harbors alone. This is in addition to supplies brought directly across the beaches, which intelligence estimates at another 5,000 to 6,000 tons daily. 12,000 tons per day," Hartmann repeated. He pulled out a file containing logistics reports from the Eastern Front. "Our entire army group there receives approximately 8,000 tons per day across our established rail network and road infrastructure. They're exceeding that through temporary facilities in a combat zone." The assessment continued through June and into July. Weber's team expanded their documentation, photographing every detail, interviewing captured Allied engineers when possible, building a comprehensive technical picture. The quality of their work was never in question. Their competence as engineers remained intact. What changed was their understanding of the strategic context. One afternoon in mid-July, Weber stood at the same clifftop position where he had first observed the harbor. 2 months had passed since the landing. The artificial harbor below was now operating smoothly, a vast industrial facility humming with organized activity. He could see clearly how the various components worked together: the breakwaters calming the sea, the piers enabling rapid cargo transfer, the beach organizations processing and distributing supplies inland. It was beautiful in a way, a magnificent example of engineering excellence applied to strategic purpose. Fischer joined him carrying the completed technical report, 732 pages, he said. Complete specifications, detailed analysis, strategic implications. "Everything we've learned about the Mulberry Harbor system. Will it make a difference?" Weber asked. "Understanding how they did it, will it help us counter it?" Fischer was quiet for a moment, watching as another convoy of trucks rolled away from the harbor, loaded with supplies that would enable continued Allied operations. "I think," he said slowly, "that the purpose of understanding isn't always to enable victory. Sometimes it's to recognize reality clearly, to stop making decisions based on wishful assessments and start making them based on truth." Weber nodded, thinking of the young engineers he had trained, the students who would need to rebuild after the conflict ended. "They're teaching us a lesson," he said. "Not about engineering, not really. About what it means when industrial capacity reaches a certain threshold, when production becomes so vast that logistics transforms from limitation into weapon." The report went up through channels, meticulously documented and brutally honest. Weber never learned how high it reached or what decisions it influenced. He knew that by the time his assessment was complete, the strategic situation had evolved beyond the point where understanding Mulberry harbors could change outcomes. The Allies were ashore in strength, supplied through multiple channels, advancing on all fronts. But for Weber personally, the experience proved transformative. Before Normandy, he had understood the conflict primarily in technical terms, believing that German engineering excellence and defensive preparations could offset material disadvantages. The Mulberry harbors demolished that comfortable assumption. They demonstrated that past a certain point, industrial capacity became its own form of military genius, overwhelming tactical excellence through sheer abundance. In August, Weber was transferred to Berlin, assigned to defensive engineering as Allied forces approached from all directions. He brought with him not just technical knowledge, but a profound shift in perspective. When younger officers proposed ambitious defensive schemes that required materials Germany no longer possessed, Weber would think of the Mulberry harbors and quietly explain why certain approaches were no longer feasible. Hauptmann Schneider ended up in British captivity after the conflict's conclusion. During his detention, he was interviewed by Allied engineers curious about the German assessment of the artificial harbors. They were surprised by the depth and accuracy of the technical analysis, impressed by the professional quality of the documentation. One British engineer, a man named Thornton, who had helped design the Phoenix caissons, spent an afternoon discussing engineering details with Schneider. "Your report was excellent," Thornton told him. "Technically accurate, strategically insightful. You understood exactly what we had built and what it represented." "Then you know," Schneider replied, "that understanding didn't help us. We could see what you had accomplished, calculate what it meant, and still couldn't respond effectively. That was perhaps the most difficult realization, that professional competence was insufficient against that magnitude of industrial commitment." Thornton nodded slowly. "The Mulberry project wasn't about building something the Germans couldn't understand," he explained. "It was about building something so large, so quickly, and with such quality that understanding wouldn't matter. We wanted your engineers to look at those harbors and realize they were facing an industrial base that could treat major engineering projects as temporary installations." Fischer returned to Hamburg after his release, finding his former shipyard destroyed by bombing. As the city began its slow reconstruction, he worked on harbor restoration projects, applying lessons learned from both sides of the conflict. He occasionally lectured at the rebuilt Technical University, using the Mulberry harbors as a case study in the relationship between engineering and strategy. "The artificial harbors taught us that technology alone doesn't determine outcomes," he would tell his students. "The Mulberry system used no secret materials, no revolutionary techniques. What made it decisive was the industrial ecosystem that could produce such infrastructure as an expendable asset. We were fighting 20th century industrial warfare with 19th century assumptions about scarcity and resource limitation." Lieutenant Richter, the practical foreman, went home to Bremen and resumed work in civilian construction. He never spoke much about his wartime experiences, but colleagues noticed he had little patience for complaints about project difficulties or resource constraints. Once, when a young engineer was frustrated by construction delays, Richter quietly described watching the Allies build a complete harbor facility in less time than the project they were discussing had spent in planning phases. "The lesson isn't that we should lower our standards," he explained. "It's that we should understand what's actually possible when competence meets adequate resources and clear purpose. I've seen what engineering can accomplish when those factors align properly." Major Hartmann survived the conflict and wrote extensively about the intelligence and assessment failures that had characterized German strategic planning. His post-war analysis, drawing heavily on Weber's Mulberry Harbor report, argued that the Reich's leadership had fundamentally misunderstood the nature of industrial warfare. They had focused on tactical excellence and operational innovation while failing to recognize that strategic success in modern conflict required industrial dominance. Weber himself lived until 1983, long enough to see Europe rebuild, to watch as former enemies became allies, to witness engineering excellence applied to peaceful purposes. He occasionally received letters from Thornton and other Allied engineers, professional correspondence between men who recognized each other's competence despite having fought on opposite sides. In his final years, Weber donated his personal papers to the Technical University of Berlin, including his original notebooks from the Mulberry Harbor assessment. Students studying engineering history would sometimes ask him about those weeks in Normandy, wanting to understand what it had been like to examine such structures while the conflict still raged. "It was humbling," Weber would tell them, "not because we couldn't understand the engineering we could, but because understanding forced us to confront how thoroughly we had underestimated what we were facing. Those harbors weren't just impressive construction projects, they were physical manifestations of an industrial and organizational capacity we couldn't match. Seeing that clearly, accepting it honestly, was perhaps the most difficult engineering assessment I ever performed. The Mulberry harbors themselves had varying fates. The American installation at Omaha Beach was largely destroyed by storms in mid-June and never fully rebuilt, its functions absorbed by other supply methods. The British installation at Arromanches, called Mulberry B, continued operation until November 1944, landing approximately 2.5 million tons of supplies and 500,000 vehicles before conventional port facilities became available. Some components of the artificial harbors remained in place for decades. The massive concrete Phoenix caissons proved nearly impossible to remove economically, and many still sit off the Normandy coast, gradually deteriorating but still visible at low tide. They became monuments not by design, but through sheer stubbornness of construction, too solid to remove, too massive to ignore. For the engineers who assessed them in June 1944, the Mulberry harbors represented something beyond military infrastructure. They were proof that industrial warfare had reached a scale that transformed traditional military calculations. Courage, tactical skill, operational brilliance, all the factors that had decided previous conflicts became insufficient against an opponent who could manufacture harbor facilities faster than they could be destroyed. Weber's report, eventually declassified and published in engineering journals during the 1970s, became a case study in military-industrial analysis. Not because it revealed secrets, the basic facts about Mulberry harbors were well documented, but because it captured the psychological impact of confronting overwhelming industrial superiority. Weber and his team had performed their professional duties excellently, producing accurate assessments and sound analysis. What they couldn't do was change the fundamental strategic mathematics that the harbors represented. The experience transformed how Weber understood his profession. Engineering wasn't just about technical excellence or innovative design. It was about the entire ecosystem of training, resources, organization, and purpose that allowed technical excellence to be expressed at meaningful scale. The Allies hadn't won through superior individual genius, but through superior systematic application of competent engineering across an industrial base vast enough to treat remarkable achievements as routine production. This lesson, painful as it was to learn through professional assessment of enemy capabilities, proved valuable in the post-war period. Weber contributed to reconstruction efforts, applying his understanding of large-scale organization to civilian projects. He advocated for systematic engineering education, for industrial planning that supported quality production, for institutional structures that could sustain excellence over time and scale. The Normandy assessment became a reference point throughout his career, the moment when he had confronted truth that contradicted comfortable assumptions and chose an honest analysis over wishful thinking. That intellectual integrity, that willingness to report reality even when reality was discouraging, represented engineering professionalism at its highest level. The students who studied Weber's Mulberry report decades later found value not just in the technical specifications, but in the methodological approach. Here was documentation of how competent professionals responded when confronted with evidence that challenged their strategic worldview. The report demonstrated that true expertise included recognizing the limits of one's own capabilities and the superior capacities of others. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.